Welcome everybody. Thanks for joining us today to learn about humidity measurement technology, pros and cons. This webinar is designed to help you make a better measurement, and one of the principles of a better measurement is to choose the right technology. That's what this webinar is about. Everyone who registered for the webinar will receive a copy of the slides and a link to the recording. We send out an email within about 24 hours of this live broadcast, and we also post the webinar recording and the slide deck on the Rotronic website. Just go to rotronic.com and look for the Measurement Academy section. Everyone is in listen-only mode. That means that you cannot speak to us directly via your computer or your telephone, but we do want to hear from you. We want this to be interactive. And the way to interact is to type questions or comments in the questions pane. If you look on your control panel, should be towards the bottom. Just go ahead and expand that and type in a question or a comment at any time. We'll have 2 Q&A sessions for this webinar, but you can type your question at any time it comes to mind. You don't have to wait till the Q&A sessions, and we'll be sure to queue those up for some answers. Once again, this webinar is being recorded and it will be made available to all people who registered. This webinar is presented and created by Rotronic Instrument Corporation. If you don't already know Rotronic, we manufacture precision measurement instruments for humidity, of course, dew point, carbon dioxide, temperature, water activity, and differential pressure. And additionally, Rotronic offers an environmental monitoring system for critical environments, both regulated and non-regulated. We don't talk about the products during this webinar because it's educational, but of course, if you do want to hear about the products, we'd be delighted to chat with you about them. Just shoot us an email or look up your regional contact on the website, and we'll answer all your questions and help you match an instrument to an application. Speaking today, my name is Bruce McDuffie. I'm with the Rotronic Marketing Department, and I've been in the humidity measurement business for about the last 10 or 11 years. I was a field sales rep, and I've seen a lot of humidity applications, done a lot of troubleshooting, so I've seen field application of technology. Michael Botzkis is your co-presenter today, and Michael is the lead metrologist with Rotronic Americas, specializing in relative humidity and temperature measurement. And Michael's been involved in manufacturing and calibration of humidity and temperature instruments for about the past 19 years. Welcome, Michael.
Thank you, Bruce. It's great to be here today.
Looking forward to it. And with that, I'm going to turn it over to Michael to walk us through the agenda and the takeaway for today.
Okay, so today we're going to start off with a parameter review, look at some of the common humidity parameters that we use to report the amount of moisture in an environment. We'll then take a look at 6 particular sensing technologies. We'll be looking at mechanical sensors, psychrometers, resistive sensors, capacitive sensors, the metal oxide, and chilled mirrors. We'll go through how each sensing technology works and then look at some pros and cons to each one so that you can look at how they would potentially fit for your own measurement applications. The key takeaway for today is to give you a little bit more information about which sensor would be best in a few specific applications, but also to help you make those decisions when you can look at the very specific requirements that you've got and then match up the best technology to that. To start with though, I believe Bruce has a few polls just to help us get to know everyone a little bit better.
Yeah, thanks, Michael. We like to make these interactive, and one of the ways we do that is to learn a little bit about our audience. And I think it's always interesting, probably for you out there listening, to know who else is out there listening today. So the first question I have for you folks is, what is your industry? And I will launch that poll. And if you can choose what is your industry, and we'll see what kind of a cross section we get out there today. If you in pharma, biotech, or food, HVAC, being a contractor or consultant? Are you in government, research, or education? Are A&E firm or something else? And the others are coming in strong. Michael, as usual. Yeah, if you just type in your the question pane, what other is, just and I'll share that with the audience too, if you don't mind doing that. Just type in your industry in the questions pane. It's like Amal
Unfortunately,
is
they
in.
only give us 5 answers here, so other
Yeah.
seems to dominate quite a bit.
Yeah, it's hard to, we've got such a broad, diverse audience. We got food, distribution coming in on the question pane, contract lab, testing lab, automotive, skateboard manufacturer. I wonder if, is that real? Some, that'd be a fun industry. Yeah, it's real. Okay, Jesse, thanks. Manufacturing with humidity controlled labs, manufacturer, distribution. Thanks everyone for sharing that. Good, nice, diverse audience. And I'll go ahead and close the poll and I'll share the results and you can all see what our diversity is today. Okay, another question, get to know the audience. What is your role? What is your particular role? Are you the boss, a facility manager, a contractor, technician, or something else? Give that a few seconds.
Now there goes out to the lead again.
Yep. We've got an inside sales manager. Didn't have that on there. Do we allow salespeople on these webinars, Michael? I guess
We let everyone come in.
we love salespeople. Test engineer, sales manager, few bosses out there, facility manager. Okay, thanks everyone. I'll close that poll and I'll share the results. And again, it's a good mix today. And I've got one more for you, quick poll before we get into the presentation. Oops, gotta hide it. What's your biggest challenge with humidity measurement technology? This can also help us tailor the presentation a little bit. But what is your biggest challenge with humidity measurement technology? Is it understanding the performance, knowing what questions to ask, finding a vendor who understands what you need? Is it something else, knowing what works for your application? What's your biggest challenge? I know those might all be challenges for you, but what's the one that vexes you the most? Give this one a few seconds and then we'll get into the presentation. Okay, thanks everyone. I'll close it out. Last chance. Okay. So knowing what works for my application. Yeah, that's tricky. And that's when you're talking about making a better measurement of humidity, that's probably the number one thing that I've seen over the years. What do you think, Michael?
It's definitely up there, knowing which instrument's going to work well and knowing the limitations of it. So how you have to deal with that in the specific application.
Yeah, I saw that in the field all the time where people had chosen the wrong instrument, the wrong technology. So let's talk about that. First thing we're going to cover is a little bit of a review of parameters, but the reason you want to understand the parameter is that each of these technologies we're going to discuss, the sensor itself measures one of these different parameters. It measures the property of one of these parameters. So for example, relative humidity, remember that's a property that's measured directly by some of this technology, and that's the ratio of the partial pressure of water vapor to the saturation vapor pressure. So it's the amount of water vapor present compared to the total potential that could be present based on the temperature. And we'll see a few technologies that directly measure that. Water vapor pressure or partial pressure of water vapor, that's an absolute measure. It tells us how many water molecules or how much water vapor by mass is actually present. And there's a technology we'll talk about that measures that. Dew point temperature is the temperature at which a moist gas is saturated over a plane of pure liquid water. Or in more layman's terms, it's the temperature at which water vapor condenses as you gradually lower the air temperature. And finally, wet bulb temperature. Wet bulb is, there's also a parameter, a measurement sensor that we're going to talk about that actually measures direct wet bulb. I guess you'd have to say two sensors. But this is the temperature as measured as water evaporates. And as water evaporates, as Michael's going to go into here in more depth, as water evaporates, it takes energy and that lowers the temperature. And that's the wet bulb temperature. So with that, we're going to talk about the first technology, which is mechanical. And you may think mechanical, boy, those aren't around anymore, but there's still some out there. You can actually still buy a hair hygrometer, but a mechanical humidity technology usually uses organic material, and that organic material changes shape based on the relative humidity. So it's measuring that property relative humidity. Typically the shape change, whatever material you're using, is connected to levers or springs or something that moves a pen like we see here, or it moves a needle, something like that. Typically you'll find hair, human hair in some cases, horse hair, things like cat gut, certain textiles, gold beater skin. One of my favorites, gold beater skin, is the inner lining of a cow's intestine. Works very good detecting relative humidity. Pros and cons of mechanical sensors. Well, you don't need electricity. You just need that organic material. They're fun. I have a whole collection of mechanical humidity instruments. So for me, it's fun. I just throw that in there. But on the negative side, they're not very reliable. You can't calibrate them well. I mean, you can calibrate anything, of course, but you can't get a low uncertainty calibration on mechanical. They're only accurate mid-range, 30 to 80%, high hysteresis, and they're really slow to respond. This one to the right here, that is a vintage Fisher hygrometer. The bottom one's the hygrometer, and that's a hair hygrometer. You could buy that on Amazon today if you chose. Use mechanical sensors when you need just a general idea, like if you need to know what the relative humidity is in your office, put one on your desk. If you don't have much money to spend, these might work. And for fun, if you're a humidity geek like myself or a humidity geek like Michael.
That's right.
And with that, I'll turn it over to Michael for a discussion about the second technology, the psychrometer or wet bulb.
So the psychrometer is a device. We don't see them around too much anymore, but they used to be very common. A manual sling psychrometer, as is shown in the center picture here. All a psychrometer is essentially is two thermometers. So we're not measuring relative humidity directly, we're measuring temperature two times. The bottom thermometer in this picture is what's called our dry bulb thermometer. And this is just measuring the ambient temperature in the environment. So just the temperature that we normally see. The second thermometer here, the one on top, actually has a sock on it, and that sock is wet. And as the water evaporates from that sock, energy gets taken up in that evaporation process, and that causes the temperature of that thermometer to drop down. So there's a depression in that temperature. And it's the temperature difference between the wet bulb and the dry bulb temperature that lets us calculate out what the relative humidity is using either a psychrometric chart, or we can use one of the many available online calculators for measuring that. So there's a couple different types of technologies for psychrometers. There's the sling psychrometer that we see here. Over on the right is an aspirated psychrometer. This one's slightly different in that it has a fan that draws the air over the psychrometer. So it makes it a little bit more repeatable and a little bit more consistent in its readings. There's a number of advantages to psychrometers. They can be very cheap to purchase. You could even build one yourself. All you need is a couple temperature probes. They work very well in environments where there's going to be condensation, since one of the probes needs to be wet anyways, and they are temperature sensors. They're pretty insensitive to either of them getting wet. The dry bulb temperature sensor, though, does need to remain dry. Otherwise, it will be giving a wet bulb reading. So if it does get condensation on it, you need to make sure that that gets dried off. It's fairly easy to convert the wet bulb, dry bulb into relative humidity using a chart, graph, or one of the calculators. The downside to psychrometers, especially the manual ones, is they do take a fair amount of skill to get a good repeatable measurement. Any variation in the airspeed over them, over the sensors, can cause the wet bulb temperature to vary. Too fast a speed and you'll get extra evaporation, causing the wet bulb temperature to go down farther than it actually should. If you're too slow, you get a little microenvironment created, and then your evaporation rate is too slow. So they tend not to give very repeatable measurements. They're also not accurate in small spaces, and this is because they're constantly evaporating water, so they're affecting the local environment. So really, there's a lot of variables that come into the psychrometer, and it ends up giving a relatively high uncertainty. Typically, we still do see these as the control sensors in some humidity chambers, especially ones that are trying to operate at very high temperatures and high humidities. So other places where we would use a psychrometer would be to understand whether evaporative cooling systems are going to be effective. There, the wet bulb temperature is an important value. We possibly use them where we've got large air samples and we don't need an overly accurate reading, or we want to be able to have something that will give us relative humidity, but again, we don't have any power available. So there's no electricity. We need to just be able to take a purely manual reading and get a value. And with that, just to make sure everyone's paying attention, we'll go to our first quiz for today.
Here it comes, folks. This is a tricky one. I'm going to give you a heads up. So give you a few more seconds to consider this one. Which one of these is not true? Which one is not true? Mechanical hygrometers are fairly accurate mid-range. Psychrometers are easy to operate for reliable measurement. A horsehair hygrometer has a slow response time. Gold beater's skin is found in mechanical hygrometers, and wet bulb is used in a psychrometer. Which one of those is not true? We should have the Jeopardy music here, Michael, but instead of bedtime, haven't been able to figure out how to do that.
Opportunity for improvement.
There you go. Responses are coming in. Looks like most folks are getting this one. Give it a few more seconds while folks think about that. Perhaps some re-engaging with us. Okay, I'll go ahead and close the poll. Last chance. Closed. The correct answer is the second one. Psychrometers are easy to operate for reliable measurement. That is not true. As Michael just said, they're difficult to operate for a reliable measurement. Some people think, well, I can just sling it around above my head and that's all it takes. It takes a little more than that. So good job. 60% got that correct. Horsehair hygrometer, those do have very slow response times. Gold beater skin is found in mechanical hygrometers. Wet bulb is used in a psychrometer, and mechanical hygrometers can be fairly accurate mid-range. Okay, thanks for sharing that information, folks. And with that, we'll talk about the next technology, which is more advanced than a horsehair hygrometer. We'll talk about resistive sensors. And a resistive sensor is measuring relative humidity directly. It's measuring that property. And it's Couple of electrodes. You can see some figures, some images here. I'm going to turn on my spotlight pointer. You can see some different types of resistive sensors here, and they all have a couple of electrodes that go onto a substrate. And the substrate might be coated with salt or some other conductive polymer. And as the relative humidity increases, then the resistance decreases. And we measure that resistance with electronics, and we have a formula for conversion from the resistance to the relative humidity. That's essentially how they work. Pros and cons for a resistive sensor. They are field replaceable, so they're easy to use that way. If they get ruined, you just pop one out, pop the old one out, pop a new one in. Pretty inexpensive. They're good for the mid-range from 20 to 90%, so like an office building or something like that. Office building not in Colorado, by the way. Today it's snowing and cold in Colorado where I am, and I measured the relative humidity in my office is about 8%. Pretty dry. Cons for resistives, they're not really suitable for extremes. If you have an office like mine that's at 8%, it's not going to be very accurate measurement. They are not resistant to harsh conditions. If they get wet or chemicals, or if they get dirty, they don't stand up very well. The repeatability, questionable, so it's not as good as other technologies we're going to talk about. And they don't like condensation at all. But use a resistive sensor when, again, conditions are moderate, 20 to 90%, when you don't expect to have condensation, and when it's not a critical measurement. Examples where I've seen resistive sensors are a clothes dryer. If you have an electric or a gas clothes dryer in your house, you can set it to turn off at a certain, usually a relative like dry or dryer or something like that. That's probably going to have a resistive sensor in it. HVAC, you can see resistive sensors are used sometimes, and if you go down to Radio Shack or you buy a $15 desk hygrometer, it's probably got a resistive sensor in it. And with that, I'm going to turn it back over to Michael to talk about our favorite technology, capacitive sensors.
So the capacitive sensor senses relative humidity directly. So everything that it's changing is due to changes in the actual relative humidity. So unlike the psychrometer where we're measuring wet bulb and calculate relative humidity, this is a direct measurement of that. So from a functional standpoint, the capacitive sensor is essentially a capacitor. Like any other capacitor, it has two electrodes separated by a dielectric layer. At least one of the electrodes needs to be porous to allow water vapor through, and where it gets absorbed and desorbed by the polymer layer. As that water vapor permeates into the sensor, the capacitance of the sensor itself changes, and it's that capacitance that we're measuring with the electronics and then converting into a relative humidity value. As the capacitance increases, that's indicating a higher relative humidity. Lower relative humidity, as all those water molecules are coming out of it, the dielectric constant is decreasing, which gives us a lower capacitance. These sensors are fairly linear in how they behave over relative humidity, but there are definitely little quirks and small curves within their response, both over humidity, and then there's also some temperature effect on them as well. Looking at the pros and cons for them, compared dollar to dollar to the other technologies, these are probably give you the best combination of accuracy and reliability for the dollar. They are fairly resistant to water, dust, and chemicals. For example, if water gets onto one of these sensors, the vast majority of them will recover. They don't need to be recalibrated. They'll just go back and start to read, give you proper readings again. They're very small in size, so they can be used to monitor small enclosures or small spaces. And they have a fairly fast response time. Response times can be as fast as 10 or 15 seconds. It is dependent on airflow over the sensor, but that's one of the faster response times that's available. They can also have a very wide range of measurement. Quite often, these sensors will be set up to measure from 0 to 100% relative humidity, but they can also be set up to monitor very low dew points or frost points. So there's capacitive sensors. They're set up to measure as dew point measurement devices, but they'll measure from very dry dew points, even down as low as -70, -80 dew point, and then up to about 10 or 20 degrees C dew point, depending on the sensor. So you can get them set up for either measuring the very low water contents or the higher ones. Typically, a lot of them have a wide temperature range. They can operate from -70 to 200 degrees C, depending on the manufacturer. Typically, this is going to be used more for the sensors that are measuring in the relative humidity ranges, the 10% up to 100% relative humidity. The cons to them is they can have limited accuracy in very dry conditions, and for this I'm referring to the sensors that are set up to measure the wide range of relative humidity, the 0 to 100. They don't give a very good indication of small changes in water content when we're at the low end of the scale. That's where one of the dew point specific sensors would be better. The resilience to chemicals is very dependent on manufacturer. Depending what's in your environment, various chemicals and vapors within the environment can cause drift in these sensors. The better manufacturers will actually provide a list of what chemicals and what concentrations the sensor can withstand before it starts to affect the readings. So this is something to really keep in mind if you're in any environment where there is some sort of contamination that might be present. And that contamination can be anything. Often I say the best sensor for contamination is our own nose. If you can smell something in the environment, there's potentially something there that to the RH sensor could be a contamination. So if you're seeing sensor drift, that's quite often the cause of it. So it could be looking at what's actually there and then perhaps choosing a different capacitive sensor. We do require electronics to monitor these sensors, and they get a little bit fancy. So it's not something most people could put together themselves. So we're dependent on the manufacturers to have all the signal conditioning in there. High temperature combined with high relative humidity can also affect the calibration on some of these sensors. Again, it varies manufacturer to manufacturer, but it's something to keep in mind if you're looking at a very high humidity at a high temperature. These tend to be a little bit more expensive than resistive sensors, but the performance that we get out of them is typically better. We're going to use or look at using a capacitive sensor when potentially we've got condensation in our environment. We're probably looking at 5 or 10% relative humidity and higher, or if we've got a dirty environment, dust around. Dust will potentially slow down the response time as it clogs pores, but that's about it. And if we need good performance, a good combination of accuracy, repeatability, and stability, that's where capacitive sensors really stand out. And with that, I'll pass it back to Bruce for our next quiz.
Thanks, Michael. And a reminder, folks, there are 5 handouts in the control panel. Just look at towards the end. It says handouts 5 of 5. There's an excellent paper in there about the capacitive sensor and how it works, and a little more about positives and negatives, as well as what goes into the uncertainty budget for a capacitive sensor. And there's 4 other great assets in there too. Just feel free to download those. There's no form, there's no anything, just download them direct to your computer. And also, as questions come to mind, again, type them in as they come to mind, because by the time we get to the last technology, chilled mirrors, you may have long forgotten about the wet bulb, for example. So we have a true and false on this one. True or false, I should have said. And the statement is, resistive sensors are better than capacitive sensors for condensing environments. Is that true or false? Or you don't know? It's okay to say you don't know. We'll just assume you were doing emails during our presentation. Resistive sensors are better than capacitive sensors for condensing environments. True or false? Give it a few seconds. Looks like most folks are getting this correct. Always glad to see that. Okay, I think everyone's voted. Last chance. 5, 4, 3, 2, 1. Closing the poll. The answer is false. Capacitive sensors are much better for condensing environments. As Michael said, they typically dry out and they come right back into calibration. The next technology we'll talk about is the metal oxide technology, or more commonly called aluminum oxide. And this is a technology, it's also a capacitor. And what you do is you take an aluminum substrate and then you anodize the aluminum. And then you put a layer of very thin film of gold on the top. And as the water vapor or the partial pressure of water vapor changes, then the amount of water molecules that adsorb onto the aluminum, the anodized aluminum, changes. And as those water molecules populate the aluminum, then the capacitance changes. These do measure directly the amount of water vapor present. They are not measuring relative humidity. If you have a metal oxide or an aluminum oxide sensor that's outputting relative humidity or dew point, that's being calculated. It takes the partial pressure of water vapor, a temperature, and usually a pressure, and calculates it. So it's an absolute measure. And again, you need temperature and pressure for conversions. Pros and cons for this one. Get my pointer going here. This technology is excellent for very dry conditions. If you have a dew point even as low as minus 100 degrees C, which is only a couple of parts per million water vapor, these work very well. They have very small footprints, so they don't take up much room at all for the sensor. However, on the con side, they're pretty slow to respond to changes. I remember years ago when I was an air compressor salesperson, and we would have to go troubleshoot one of our dryers, a desiccant dryer. We'd bring in the aluminum oxide hygrometer, and we would let that stabilize for 24 hours before we could come back and actually get a reliable reading on the dew point. Now, I'm not saying they all take 24 hours, just saying they do tend to respond slowly to changes. If they get wet, they're done. They have to be recalibrated. They do require a lot of maintenance, frequent calibrations, because they're not very stable over time. And the calibration is usually pretty expensive and time consuming, so usually you have to have a loaner if you're using it in some type of process. So choose metal oxide when you have a very dry, very clean air or gas. They work very well there. If you have a dew point that's steadily less than minus 70 degrees C, it could be a good choice. If you have stable, uneventful airstreams, in other words, you're not going to get condensation or other dirt in that airstream, they can be very good. And if you're measuring trace moisture, you need like a ppm or even in some cases a ppb output. They can be good choices. and we'll move on to our last technology, which is chilled mirrors. Michael?
So the chilled mirror fundamentally measures dew point. It's not measuring relative humidity. If we're getting any of those values out of it, those are being calculated. So in order to measure dew point, what it has is basically a mirror. It's called a chilled mirror because there is a mirror in it, and that mirror is being chilled. So it's got a mirror, and it's got a cooling system built onto that mirror to draw the temperature down to the point where water or moisture will condense on that mirror. So there needs to be a steady flow of air or whatever gas we're trying to measure the humidity in going across the mirror at all times. There's then a light, typically an LED, that shines on the mirror, and then a receiver that measures the intensity of light being reflected off the mirror. As dew or frost form on the mirror, that the light being sensed by the receiver goes down, and that's how the system knows that we've now hit the dew or frost point. So we are getting a fundamental measurement in that we're creating a dew point. We're actually measuring dew point, and we measure this by measuring the temperature of the mirror. So once we know we've got dew or frost forming on that mirror, we're measuring the temperature. The diagram doesn't show it, but there would actually be a temperature sensor embedded here, and that's how we know what the dew point or frost point is. Now, looking at the pros and cons for this technology, let me get over to the next slide. Chilled mirrors typically are going to be the most accurate of the humidity measurement devices that we've talked about today and have the lowest uncertainties. The uncertainty for these mirrors can be as low as plus or minus 0.1 degrees C dew point, which is about as good as we can get for most commercial and industrial applications. They are highly stable. Since we're talking about temperature sensors being our measurement technology, those can be made to be very stable over long term. I've had chilled mirrors going for calibration annually over the period of about 10 years and never actually had the values adjusted. Some of them can be that stable. They operate over a very broad measurement range. They can be used down to minus 100 degrees C dew point or frost point, depending on manufacturer and configuration, and then operate all the way up to 100 degrees C, again, dependent on the specific model. There are some cons to this technology. There's a reason why you don't see everyone using them, and probably the biggest reason for that is they are definitely more expensive than the other technologies. Typically, even the lower cost chilled mirrors, they're starting at where the high-end capacitive sensors stop. So almost always you'll find a capacitive system for less than a chilled mirror system. These do require a fairly clean environment. If dust or other particles are landing on the mirror, there's no way for the mirror to know the difference between dust or water vapor. Some of them have some tricks to try to make that determination, but it is important to keep that mirror clean. And it's that keeping the mirror clean that creates a higher level of maintenance for these devices versus some of the other devices we've talked about today. The mirrors do need to be cleaned on a regular basis and make sure that when they're being cleaned, we're not leaving streaks or other things behind. And so this can require a skilled operator to be the person taking care of and using the chilled mirror. We also need to make sure we've got steady airflow through the sensing head. Otherwise, we don't know what's going on in the environment around us. So typically, we're going to use a chilled mirror where we need to have a very low uncertainty and high stability in our measurements. And this is typically going to be a lab or research and development type environment. We want to know that our environment is clean and controlled. Quite often we say, well, if you got a lot of budget room and you need to use it, a chilled mirror is a good way to go. Not all of them are that expensive. Some high-end server rooms might use a chilled mirror in them as well. Typically, they're not recommended for inline or field applications, though. With that, I'll pass it back to Bruce for our final quiz.
Okay, last quiz is about which technology is most accurate. See the poll now. Which of these technologies that we've discussed is the most accurate? The only one we didn't put on there is as a choice is the mechanicals, because let's just stipulate that that's the least accurate. Give it a few seconds. Folks are voting. Looks like most people are getting this one right. And in the meantime, go ahead, Michael.
I was going to say, of course, accuracy comes down to how you've got the instrument calibrated, but from a fundamental capability, that's what we're looking at here.
Okay, looks like everyone has voted. I'll close the poll. And I will share the results. We can see the correct answer is chilled mirror. Chilled mirror is the most accurate technology. And again, granted, we could argue about the term accuracy, but for the sake of this one, we're saying chilled mirrors. At plus or minus 0.1 degrees C is the dew point accuracy and the best ones. Okay, we'll hide those results and we're going to go into an overview. Michael, let's have an overview of what we talked about as far as technologies go.
So we really only looked at 6 different technologies today: the mechanical, psychrometers, resistive and capacitive sensors, the metal oxide, and the chilled mirrors. There are a lot of other technologies out there that can be used for measuring relative humidity or water content. There's spectroscopy, there's color changing chemicals. Often you'll see those just in the little strips put in with packages, and if it's one color, it's gone beyond the relative humidity limits. There's saturated lithium chloride, there's electrolytic sensors. Gravimetric is actually where you're pulling the water content out of the air and then weighing it to understand how much water content is there. And that actually the NPL lab, it's the NIST equivalent over in the UK, they've got a system set up for doing that, and that's one of the lowest uncertainty relative humidity measurements available worldwide. But the 6 that we mentioned, those are probably the most common ones that you're going to come across in your typical applications. And with that, I believe we move into a question period. Bruce, do we have any questions?
Yes, we do have some questions. And folks, don't go anywhere, because we have this Q&A session and we have another Q&A session. And in between, we're going to look at 3 different application examples on how to go through briefly the process of choosing the right technology. So don't sign off yet. And the first question we have is from Gregory. And Gregory says, why do you say capacitive sensors measure RH directly when they really measure capacitance? What do you think about that one, Michael?
I guess that's a fair question. We say they measure relative humidity directly because the sensor is changing according to what the relative humidity is. So rather than it measuring the dew point temperature or the wet bulb temperature, it's affected by what the relative humidity is, and that's why I say we're measuring relative humidity. In the same way for temperature, we're not actually measuring temperature directly out of a temperature probe. If it's a PRT or a resistive sensor, we're measuring resistance. So we're not talking about what the electronics is measuring, we're talking about what is affecting that particular sensor type. And that's why we say we're measuring relative humidity directly.
Okay, how about this one from Gene? What is the best way to protect the capacitive sensor to prevent dust or product from getting onto the sensor?
A bunch of manufacturers have various screens or filters that can go over the sensors. Those will protect the sensors themselves from particular contamination, so particles, dust, that sort of thing. So those are very effective for that type of contamination. You do just have to be careful. The better the filter, the slower the response time of the sensor, because of course now it takes longer for the air to work its way through that sensor, or through the filter to the sensor. When it comes to vapor contamination, there's not a whole lot that can be done to protect the sensors. In those cases, it's really looking for a sensor that can handle whatever type of vapor is present. And this is where it becomes very manufacturer dependent on the performance, and even within a given manufacturer, they might have a couple different sensors, and depending on the application, you might choose one sensor or the other.
And I would add into that question, this is the challenge, and this is one of the things that makes measuring relative humidity or humidity in general so challenging, because whatever the sensor is, it has to be in the environment. It has to be exposed to the environment. Unlike temperature, you can hermetically seal a temperature sensor and still get an accurate reading. But humidity is right out there in whatever's in the environment. So it is one of the main reasons why measuring humidity reliably is so difficult. Okay, Michael, this one, oh, Rebecca, yes. Rebecca says, will we get the slide deck? Yes, everybody will get a link to the recording and will get a copy of the slide deck. There'll be a link in the email for that download, and also it'll be on the website. And Rebecca has a question about humidity as well. This is a good one, Michael. Why is it important to measure humidity?
Because we want to know. There's a number of different reasons, and it varies for the applications. If we're talking about an HVAC system, potentially we want to understand, have some enthalpy calculations built in to help us with our energy efficiency, so that we can optimize everything within our cooling systems, to understand when we want to draw in outside air to help with cooling and when we don't, and that relative humidity plays a big part in that. Potentially we have in pharmaceuticals, if we're building or if we're making a product that's powder based, as the relative humidity changes or goes above certain thresholds, the powder might start to clump, and that could affect the dosages. Relative humidity can, it affects us in a number of ways, and it goes down to the different applications, and based on those, there is something that relative humidity is going and affecting. And so that's why we want to measure it.
Here's a bit of an application, Michael.
Mm-hmm.
Let's see, it starts, need to control test cell humidity ratio, meaning grains per pound. What would you recommend measurement? What would the recommended measurement be, and what is the most accurate property to convert?
That's an interesting question. So grains per pound, we can't measure directly. That's something that's always going to be calculated. The best technology, given the information we've got right now, I couldn't say which one's going to be the best. But I will say that whichever sensing technology we start with, and I'm going to guess it's probably going to be a capacitive sensor or a chilled mirror in this particular case, it's very important for us to understand what other parameters affect the calculation. So is temperature included in that calculation? If it is, we need to know the temperature value very accurately. Is pressure included in the calculation? If so, we need to understand what the actual pressure is and what the errors in our pressure readings are. Any errors in those other parameters will affect our calculated value. So it's very important to understand if we've got a measured value, measured directly, or if we've got a calculated value. And if it's calculated, those other parameters are critical to us getting a good reading of our calculated value.
These are great questions, folks, and we've got a bunch more in the queue, but we need to move on to this final section. And then again, we'll have another Q&A session here at the end. So we'll take some of these other great questions. So keep them coming. And with that, we're going to move on to the application examples. And again, we have 3 applications we're going to go through briefly. Granted, this is going to be very brief, but it'll give you an idea of the thought process. First one is a glove box chamber. Michael, how would we go through this one?
So what we need to do first is understand what the requirements of our system are. In this glove box, we've been given some parameters. We know we've got 5 parts per million water vapor, so a very low water content. The air is clean. We've got a minimal chance of condensation. Big part of that is because of the low water content. But we've been told this needs to be a very highly accurate measurement. Reliability and stability is critical. This is a humidity in this particular example, very important for us, to the point where for a change we've been told we don't have a budgetary constraint on us. So given that we're talking about low humidity values, we're looking at either chilled mirrors, capacitive sensors, the ones specifically done for the low humidity values, or potentially metal oxide. I would take off the metal oxide right away, just because we probably want something that can respond quickly. So that one would take that out. And after that, we need to take a close look at what the actual accuracy requirement is to choose between the chilled mirror or the capacitive sensor. Given that reliability and stability is paramount, I'd probably be leaning towards a chilled mirror just because they tend to be a little bit more stable over time. And we don't know if there's any type of vapor contamination in here. So a chilled mirror is probably going to be our best bet in this case. Bruce, can you lead us through compressed air systems?
Yes. This application, we're talking about a compressed air system. I'm going to get the pointer going here. In this particular case, it's a dry system. The desiccant dryers dry the air ideally to minus 40 degrees C dew point, which is very dry. We're operating at 90 PSI gauge. It's an industrial environment, meaning it's probably not very clean. We are likely to get condensation because the dryers are old and they tend to be unreliable. So when they break down, condensation occurs. We need to have an inline measurement because we have critical points of use, and it's a low budget operation. So this company does not want to spend too much money. So the first thing we want to take into account is the dry conditions. And recalling of our technologies that we reviewed, the ones that work well in dry conditions are metal oxide or aluminum oxide, the chilled mirror, and then the capacitive sensor, which a capacitive sensor has to be specially modified to detect very dry conditions, but there are some on the market there. So those are the 3 that can measure dry conditions. We're going to say no to the resistive, no, of course, to the mechanical, and no to the wet bulb. The next thing we note here is that they need inline measurement. That means they need to be able to put the sensor directly under pressure in line. And that being the case, we're probably going to remove the chilled mirror, because chilled mirrors, if they are used on compressed air systems, they will take a sample, and they also don't work well in dirty environments. So chilled mirror is out. Aluminum oxide, because of the condensation, we're going to remove that one. And also, typically, aluminum oxides are not inline. They do take a sample. And the other critical point is, as I just mentioned, condensation. Aluminum oxide don't like condensation, and that leads us to choose the capacitive sensor. So a modified capacitive sensor, and it's very important to get one that is modified so it can detect accurately low dew points. And that's how we would go through that selection process. And the last one is going to be an HVAC application. Michael, how would we go through this one?
So again, here we want to start with what we know. In this case, we're in a very dry climate in the US, probably looking at Bruce's office today. We've got lots of people around during the day, so we know we will be generating humidity. People are probably one of the most common humidity generators around. As we're breathing out, there's a lot of moisture in that air. We're running off a central control system, so we probably want to get some feedback back to that system. We have a relatively small maintenance staff, so we need whatever sensing system we've got to be low maintenance. And we know we're humidity controlled. So probably what we're looking at here in this application, we probably also have a fairly limited budget. We're in a dry system, so we don't really want the resistive sensors. Mechanical sensors aren't going to be able to send information back to a central control system typically. Those you're just going to read directly. A chilled mirror system, probably overkill for what we want to measure here, and cost is also going to be a concern on that, as well as the maintenance. A psychrometer, again, we're probably not going to be able to send that back to our central system. So that really leaves us with a capacitive system. And quite often here, we might also want to be looking at a real-time monitoring system. And most of the systems available on the market link up with capacitive sensors. So for this type of application, we're probably looking at a capacitive sensor, and that's where we'd start. And that's vast majority of the industrial applications for this type of monitoring for relative humidity in either HVAC or a process. Quite often we're looking at those capacitive sensors. And with that, we'll move into our last question period.
We have time for probably 2 more questions, Michael. And let's see how, depending on how your answers do.
Okay.
What is the best sensor you recommend for measuring RH inside of an air handling unit and measuring the wet bulb component of the enthalpy? This is from Gene.
For that, I think the most common sensor is going to be the capacitive sensor. There are a number of different advantages to it, but typically it's easiest for us to get the data out of and into one of our control systems. So typically that's going to be a capacitive sensor. They're going to be good and reliable, get a reasonably accurate reading, good enough for what we're looking at. And we'll also typically have a temperature sensor in the same unit as those, which we need for our enthalpy calculations.
And last question, this is from Roger. What is the best sensor type for a handheld RH meter for building condition surveys?
Again, there I would go with the capacitive sensor, primarily due to the wide range of humidities that we could see in that building. We want to make sure we can cover everything from places where when it's very cold, we get very low humidity inside that building. So we want to be able to cover the whole range of relative humidities. So the capacitive one is going to be the easiest for us to get that whole range of measurements and get a very quick and accurate reading for it.
Agreed. I agree with all of those answers, Michael. And with that, let's go ahead and wrap it up, folks. We have one more slide here. And the next webinar, it's going to go along nicely with this one, where we're choosing technology, and the previous one where we talked about making a better measurement, the theory. This will be the third sort of a capstone. How do you choose the best fit humidity instrument? And we'll look at theory, we'll look at technology, we'll look at applications, and we've got 10 points where we're going to walk you through so you get the single best instrument for your application. And again, this is the most common reason, one of the most common reasons for making a poor or not reliable humidity measurement is not choosing the best instrument or not choosing the best technology. So you can register for that one. It's on January 18th at 1 o'clock Eastern Time. Thank you very much for joining us today. If you'd like to contact us directly, you can email us at info, or you can look us up your regional contact on the website. Thank you, Michael, for those great answers and that good information.
Thank you, Bruce, and thanks everyone for attending.